Chapter 2. Inorganic Chemistry. Periodic Properties. The concept of periodicity has acquired the key position in the study of inorganic chemistry. No other generalization competes the periodic table of the elements in its ability to simplify, systemize, and rationalize known chemical facts. At present, about 112 elements are known which have numerous properties and form millions of compounds. The periodic classification of elements has extremely simplified their study. Many different forms of the periodic table have been proposed depending upon the purpose for which the table is used. However, the most commonly used form is known as long form of periodic table. Let us briefly recapitulate the development of periodic table. Its salient features as already studied in earlier classes and important periodic properties and their applications. Development of the periodic table. Since the beginning of the 19th century, scientists have been trying to find a basis of grouping elements having similar properties, though several scientists, namely Lavoisier, Dauvergne, Newlands, Mayer, and Mendeleev, attempted to find certain regularities among elements. The first important attempt to divide the elements on the basis of their physical and chemical properties was made by a German chemist Lothar Meyer and a Russian chemist Dmitry Mendeleev. They observed that when the elements are arranged in the order of increasing atomic weights, the elements with similar properties recur at regular intervals. Mendeleev gave a law known as periodic law. The law states that the physical and chemical properties of elements are periodic function of their atomic weights. The Mendeleev's classification gave him so much confidence that he boldly left certain spaces or gaps for undiscovered elements. By considering the properties of the adjacent elements in his table, he predicted the properties of these undiscovered elements. Later on, when these elements were discovered, their properties were found to be exactly similar to those predicted by Mendeleev. For example, gallium and germanium were not discovered at that time. When Mendeleev formulated his periodic table, he not only predicted the existence of these elements, but he also estimated their properties. He named these elements as Ica aluminium and Ica silicon because he believed that these would be similar to aluminium and silicon respectively. When chemists discovered these elements, Mendeleev's prediction of their property proved to be remarkably correct. Modern periodic law. In 1912, Moseley showed that the physical and chemical properties of the atoms and of the elements are determined by their atomic numbers and not by their atomic weights. Their acceptance of atomic number as the important characteristic of an atom led to the modern periodic law, which may be stated as the physical and chemical properties of the elements are periodic function of their atomic numbers. Consequently, when the elements are arranged in the order of their increasing atomic numbers, it is observed that the elements of similar properties recur at regular intervals or periodically. As a result of this, the elements fall in certain groups and lead to an arrangement called the periodic table. With the modern periodic law as the guiding principle, many new forms of the periodic table have been proposed. However, the general plan of the table has remained the same as proposed by Mendeleev. Of these, the most commonly used form is known as long form of the periodic table. The long form of the periodic table. Position of elements in the periodic table. The most widely used periodic table these days is the long form of periodic table. This is constructed on the basis of repeating electronic configurations of the atoms when they are arranged in the order of increasing atomic numbers. Long form of periodic table is given on next page. Structural features of the long form of periodic table. The long form of the periodic table consists of horizontal rows called periods and vertical columns called groups. These are discussed below. Periods. A horizontal row in the periodic table is called period. In terms of electronic structure of the atom, a period constitutes a series of elements whose atoms have the same number of electron shell. That is principal quantum number. There are seven periods and each period starts with a different principal quantum number. Elements of first period. The first period corresponds to n is equal to 1, where n stands for principal quantum number, is unique because it contains only two elements. This is not surprising because first energy shell has only one orbital, that is 1s, which can accommodate only two electrons. This means that there can be only two elements in which 1 and 2 electrons are present in first energy level. The first period contains hydrogen 1s1 and helium 1s2. Elements of second period. The elements of second period. Elements of second period. The second period contains 8 elements because for n equal to 2, there are 4 orbitals, 1 2s and 3 2p. In all, these 4 orbitals have a capacity of 8 electrons and therefore second period has 8 elements in it. It starts with lithium Z equal to 3 in which 1 electron enters the 2s orbital. The period ends with neon Z equal to 10 in which the second shell is complete 2s2 2p6. Elements of third period. In third period, corresponding to n equal to 3, there are 9 orbitals, 1 3s, 3 3p and 5 3d. However, we know from energy level diagram for multi-electron atoms that 3d orbitals are higher in energy than 4s orbitals. Consequently, 3d orbitals are filled after filling 4s. Hence, this period involved the filling of only 4 orbitals, 3s and 3p, and contains 8 elements from sodium Z equal to 11 to argon Z equal to 18. Elements of fourth period. The fourth period, corresponding to n equal to 4, involves the filling of 1 4s and 3 4p orbitals. 4d and 4 orbitals are higher in energy than 4s orbitals and are filled later. In between 4s and 4p orbitals, 5 3d orbitals are filled which have energies in between these orbitals. Thus, in all 9 orbitals are to be filled and therefore there are 18 elements in fourth period from potassium Z equal to 19 to krypton Z equal to 36, where Z is atomic number. Elements of fifth period. The fifth period, like the fourth period, also consists of 18 elements. It begins with rubidium Z equal to 37 and filling of 5s orbitals and ends at xenon Z equal to 54 with the filling up of the 5p orbitals. Elements of sixth period. The sixth period contains 32 elements Z equal to 55 to 86 and successive electrons enters into 6s, 4f, 5d and 6p orbitals in that order. It starts with cesium Z equal to 55 and ends at randon Z equal to 86. Then on the next page we have long form of the periodic table in which there are 18 groups and 7 periods. Let's talk about first group. Hydrogen, then lithium, Na, potassium, rubidium, cesium, francium. Second group contains beryllium, magnesium, calcium, strontium, barium, radium or randon. Then whole periodic table in which we are having 18 groups and 7 periods. Let's discuss about all the elements in the periodic table. The first two groups are known as S block and then the middle 10 groups are known as D block and then the rest of the other groups left are in the P block. We also have two lines downwards that are lanthanides and actinides. For S block elements, the representation is given in the periodic table. Then let's discuss about all the elements about their series atomic numbers. Hydrogen, helium, lithium, beryllium. In first period, we are having two elements, hydrogen, helium. In second period, we have 8 elements. Lithium having 8 elements, sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine, argon. In fourth period, we are having 18 elements, that is potassium, calcium, scandium, titanium, vanadium, chromium, manganese, iron, nickel, copper, zinc, gallium, germanium, arsenic, selenium, bromium, krypton. Then fifth period we are having 18 elements, rubidium, strontium, yttrium, zirconium, niobium, molybdenum, technetium, ruthenium, palladium, silver, cadmium, indium, tin, antimony, tellurium, iodine, xenon. In sixth period we are having 38 elements, from which 57 to 71 atomic number are known as lanthanides, which are given below the periodic table. So in this period there are 18 elements left, which are cesium, barium, lanthanum, hafnium. No, lanthanum is not present in this. Hafnium, tantalum, tungsten, rhenium, osmium, platinum, gold, mercury, thallium, lead, bismuth, polonium, astatine, radon. Then in seventh and last period there are also 38 elements, but from 89 to 103 atomic number, that are known as actinoids, and they are also given below the periodic table. Rutherfordium, that are francium, radium, rutherfordium, dubnium, ciborium, borium, hasmium, dermastridium, rongestrigium, copernicium, nihonium, flerovium, mosovium, livormonium, tennessine, oganesson. Now the lanthanides and actinides are given below the table. That are, firstly let's discuss about lanthanoids. Lanthanum, cerium, parasodinium, neodymium, promethium, europium, gadolinium, terbium, dysprosium, holmium, erbium, thulium, ytterbium, lutetium. Then actinoids: actinium, thorium, protactinium, uranium, neptunium, americinium, cerium, berkelium, californium, einsteinium, fermium, mendelium, nobelium, lawrenceum. So this was our periodic table. The next, elements of seventh period. The seventh period, though expected to have 32 elements, is incomplete and contains only 23 elements at present. This also provides a theoretical justification for periodicity occurring at regular intervals of 2, 8, 8, 18, 18 and 32. These numbers, that is 2, 8, 18 and 32, are called magic numbers. The first three periods containing 2, 8 and 8 elements respectively are called short periods. The next three periods containing 18, 18 and 32 elements respectively are called long periods. The number of elements and the corresponding orbitals being filled are given in the table. Like first period, orbital being filled up is 1s. Number of electrons or elements in the period are 2. In the second period, orbitals being filled up are 2s and 2p. Number of electrons present are 8. In third period, orbitals being filled up are 3s, 3p. Number of electrons or elements in the periods are 8. In fourth period, orbitals being filled up are 4s, 3d, 4p, and number of electrons that are filled are 18. Fifth period, orbitals being filled up are 5s, 4d, 5p. Number of electrons or elements in the periods are 18. Then sixth period, 6s, 4f and the number of electrons or elements in the period are 32. In 7th period, orbitals being filled up are 7s, 5f, 6d, 7p. Number of electrons or elements in the period are 32. Now, groups. A vertical column in the periodic table is known as group. In terms of electronic structure of the atom, a group constitutes a series of elements whose atoms have the same outermost electronic configurations, but they have different number of total electrons. There are 18 groups in the long form of periodic table. According to the new recommendations of International Union of Pure and Applied Chemistry, that is known as IUPAC, the group are numbered from 1 to 18. Previously, these were numbered only from 1 to 8 as A and B groups. Both the systems of numbering the groups are given in the periodic table. However, the old convention is still used in many books. The first two groups on the extreme left and the last six groups on the extreme right involves the filling of s and p orbitals respectively. These groups represent the main groups of the periodic table and are numbered as 1, 2, 13, 14, 15, 16, 17 and 18 corresponding to general configurations of NS1, NS2, NS2, NP1, NS2, NP2, NS2, NP3, NS2, NP4, NS2, NP5, NS2, NP6 respectively. The elements present in these groups are known as normal or representative elements. The first three periods containing 2, 8 and 8 elements involves the filling of only s and p orbitals. But the fourth period involves the filling of 3d orbitals also, and this results into 10 more groups. These 10 groups lie in between first 2 and last 6 groups. Between groups 2 and group 13, because 3d orbital are filled after 4s but before 4p orbitals. These were usually labeled as B group. The elements present in these groups are called transition elements. The name is derived from the fact that they represent transition, that is change in character from reactive metals. Elements of group 1 and 2 on one side to the non-metals, elements of group 13 and 18 on the other side. The designation of group as A or B is purely arbitrary. The assignment of all the transition metals to B group has an internal consistency as well as historical precedent. However, IUPAC has recommended that the groups be numbered 1 to 18 left to right from the alkali metals that are of group 1 to the noble gases that is of group 18. There are two more rows at the bottom of the periodic table. These rows consist of 14 elements after lanthanum Z equal to 57 and 14 elements which follow actinium Z equal to 89. These are placed separately to avoid undue sidewise expansion of the periodic table. The element in the first row starting from lanthanum are called lanthanides or lanthanoids, and the elements present in the second row starting from actinium are called actinoids or actinides. These lanthanides and actinides together are called inner transition elements or rare earth metals, and these are built up by filling of f orbitals. It is important to note from the above discussion that the first two groups, the last 6 groups and 10 groups in between these two extremes and 14 small groups at the bottom of the periodic table corresponds to the maximum number of electrons which may be added to s, p, d and f orbitals respectively. Discovery of nomenclature of elements with atomic numbers more than 100. The first scientific attempt to prepare the elements beyond uranium were made by Enrico Fermi and co-workers in 1934. They irradiated uranium with slow neutrons and found several radioactive products which were found to be due to new elements. The continued effort of scientists led to many new elements. These were called transuranium elements. Today, we have elements up to 112. These elements were earlier named traditionally by its discoverer or discoverers. However, in recent years, disputes regarding the original discoveries of some elements of atomic number 104 and above have arisen. After several years of discussions by the Commission in Nomenclature of Inorganic Chemistry, that is CNIC, and comments of chemists around the world, IUPAC in 1997 gave the approved official names for elements with atomic numbers 104 to 109. However, the names of elements with atomic numbers 110 and above have yet to be officially announced. To solve the problem, IUPAC recommended the nomenclature to be followed by naming these new elements until their names are officially or recognized. This nomenclature is based on the Latin words for their numbers. For example, nil for 0, un for 1, and so on as given below. For 0, root name is nil, abbreviation is n, small n. Then for first one digit, un is root name and abbreviation is small u. For 2, by is root name and b is abbreviation. For 3 is try, the root name, and small t is abbreviation. For 4, quad is root name and abbreviation is small q. For 5, pent is root name and small p is abbreviation. For 6, hex is root name and small h is abbreviation. For 7, sept is root name and small s is abbreviation. For 8, oct is root name and small o is abbreviation. For 9, ENN, N is root name and small e is abbreviation. The names are derived for combining together the roots in the order of digit which make up the atomic number, and em is added at the end. For example, for atomic numbers 104, the name may be written as un for 1 plus nil for 0 plus quad for 4 plus em, that is unnilquadium, and is assigned the symbol UNQ. At present, 114 elements have been discovered. These are elements with atomic number up to 112, 114 and 116. Elements with atomic number 113, 115, 117 and 118 are not yet known. Of course, the quest of scientists to make new elements is continuing. The IUPAC names for the elements with atomic numbers more than 100 are given below. Atomic number for 101, name is unnilbium. 102, unnilbium. 103, unniltrium. 104, unnilquadium. 105, unnilpentium. 106, unnilhexium. Likewise, all the numbers are given up to 118. Classification of elements into S, P, D and F blocks. The long form of the periodic table can be conveniently divided into 4 main blocks. In these divisions, the elements which involve the filling of particular orbital, that is S, P, D or F, are grouped together as shown. First, S block elements. The elements in which the last electron enters the s orbital of their outermost energy level are called s block elements. It consists of elements of group 1 and 2 having the ground state electronic configurations of outermost shell as ns1 and ns2 respectively, where n stands for outermost shell energy. The element corresponds to Ns1 configuration are called alkali metals, while those corresponding to Ns2 configuration are called alkaline earth metals. Thus, the general electronic configuration of S block element may be expressed as Ns, and on the above we write the number of electrons, that is 1 to 2. So the exact representation is Ns 1 to 2. Then p block elements. The elements in which the last electron enters the p orbital of their outermost energy level are called p block elements. The elements of group 3a or 13 to 8a or 18 involving addition of 1 ns2 np1, 2 ns2 np2, 3 ns2 np3, 4 ns2 np4, 5 ns2 np5 and 6 ns2 np6 in p orbitals and s orbitals are already filled in their atoms constitute p block. The general electronic configuration for the atom of this block may be written as ns2 np126. D block elements. The elements in which the last electron enters the d orbital of their last but one called penultimate energy level constitute d block elements. This block consists of the elements lying between s and p block starting from 4th period and onwards. They constitute groups 3b to 8b and 1b and 2b or 3 to 12 in the periodic table. In these elements, the outermost shell contains 1 or 2 electrons in their s orbitals ns, but the last electron enters the last but 1d subshell, that is n-1d. The general configuration for the atom of d block may be written as n-1d, electrons in it is from 1 to 10, ns 1 or 2. Thus, it is the d orbital which is progressively being filled in the elements of this block. These elements are called transition elements. The d block comprises 3 complete rows of 10 elements involve the filling of 3d, 4d and 5d orbitals respectively. These series are called transition series. First transition series, scandium Z equal to 21 to zinc Z equal to 30. 3d orbitals are gradually filled. Then second transition series, yttrium Z equal to 39 to cadmium Z equal to 48. 4d orbitals are gradually filled. Third transition series, lanthanum Z equal to 57, hafnium Z equal to 72 to mercury Z equal to 80. 5d orbitals are gradually filled. Fourth, that is F block elements. The elements in which the last electron enters the F orbital of their atoms are called F block elements. These elements, the last electron is added to the third to the outermost called anti-penultimate energy level n-2f. These consist of 2 series of elements placed at the bottom of the periodic table. The first series follows lanthanum, that is Z is equal to 57, and the elements present in the series are called lanthanides. They are also known as rare earth metals. The second series follows actinium, that is Z equal to 189, and the elements present are called actinides. They are of radioactive nature. The general electronic configuration of F block elements may be written as n-2 F 1 to 14, n-1 D 0 to 1, ns2. For example, for lanthanides, the general configuration electronic configuration is 4f 1 to 14, 5d 0 to 1, 6s2, while for actinides it is 5f 1 to 14, 6d 0 to 1, 7s2. The elements included in these two series are called inner transition elements because they form transition series within the transition elements of D block. Causes of periodicity. The recurrence of similar properties of the elements after certain regular intervals when they are arranged in the order of increasing atomic number is called periodicity. The classification of the elements in certain families was based upon the observed similarities in the physical and chemical properties. But why do certain elements exhibit similar properties and why do the similar properties recur at regular intervals of atomic numbers? Were some important questions yet to be answered. We know that an atom consists of nucleus surrounded by electrons. In ordinary chemical reactions, the nuclei of the atoms do not undergo any change, and therefore it is the distribution of the electron in various shells of their atoms that determine the physical and chemical properties of the elements. Further, it has been also found that the properties of atoms do not depend so much on the arrangement of electrons in their inner shells. Thus, it must primarily be the arrangement of electrons in the outermost shell, called the valence shell, that determines the properties of the atoms. For example, the electronic configuration of the atom of alkali metal groups shows that they all have one electron in the s orbital of the outermost valence shell, preceded by the noble gas configuration ns2 np6, but for lithium ns2 the general electronic configuration of these may be written as noble gas ns1, where n stands for principal quantum number. Electronic configuration of alkali metals. For lithium, atomic number is 3, electronic configuration 1s2 2s1. Sodium, atomic number is 11, electronic configuration is 1s2 2s2 2p6 3s1. For potassium, atomic number is 19, electronic configuration is 1s2 2s2 2p6 3s2 3p6 4s1. For rubidium, atomic number is 37, electronic configuration is 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 5s1. For cesium, atomic number is 55, electronic configuration is 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 4d10 5s2 5p6 6s1. For Fr, that is francium, atomic number is 87, electronic configuration is 1s2 2s2 2p6 3s2 3p6 3d10 4s2 4p6 4d10 5s2 5p6 6s2 4f14 5d10 6p6 7s1. Thus, the cause of periodicity of the property of elements is the repetition of similar electronic configurations of their atoms in the outermost energy shell or valence shell after certain regular intervals. Periodic properties. There are many physical and chemical properties of elements which show periodic variation with atomic number. Some of these properties, such as valency, atomic size, ionization energy, and electron affinity, are directly related to the electronic configuration of the atom, while some properties such as melting point, density, etc., are indirectly related to the electronic configuration. Atomic radii. This is very important property because many physical and chemical properties are related to atomic radii. Generally, the term atomic radius means the distance from the center of the nucleus to the outermost shell of electrons. If the atom is assumed to be spherical, it is the radius of the sphere. However, the absolute size of an atom is difficult to be defined because of the following reasons. First, according to the probability picture of electrons, an atom does not have well-defined boundary. The probability of finding of electron is never zero, even at large distances from the nucleus. Second, it is not possible to isolate an atom and measure its radius. The probability distribution of an atom is also affected by the presence of other atoms in its neighborhood. Therefore, the size of atom may change in going from one set of environment to another. Thus, we can only arbitrarily define atomic radius as the effective size, which means the distance of closest approach of one atom to another atom in a given bonding situation. In other words, atomic radius corresponds to the limit of approach of another atom in a particular substance. Therefore, the atomic radii may be called as covalent radius, van der Waals radius, ionic or crystal radius, etc., depending upon the type of bonding. First, covalent radius. The radius of an atom is calculated by measuring the distance between the centers of two atoms, that is internuclear distance, in molecules with the help of X-ray diffraction or spectral studies. In the case of homonuclear diatomic molecules, the atomic radius is defined as one half of the distance between the centers of nuclei of two similar atoms bonded together in a molecule. The radius is also called covalent radius because the atoms in a homonuclear diatomic molecule are held together by covalent bonds. For example, the internuclear distance between the two atoms in H2 molecule is 0.74 angstrom. Therefore, atomic radii of hydrogen is equal to 0.74 angstrom divided by 2, that is 0.37 angstrom. Similarly, the atomic radii of fluorine, chlorine and bromine are 0.64 angstrom, 0.99 angstrom and 1.14 angstrom respectively, because the internuclear distances in F2, Cl2 and Br2 are 1.28 angstrom, 1.98 angstrom and 2.28 angstrom respectively. In the case of heteronuclear diatomic molecules containing different atoms, it has been observed that when the covalent radii of different atoms joined by single covalent bond are added, the resulting value agrees fairly well with the experimentally determined internuclear distances of the molecule. For example, the internuclear distance in HCl molecule can be calculated by adding the covalent radii of H and Cl as radius of HCl is equal to radius of H plus radius of Cl equal to 0.37 plus 0.99 equal to 1.36 angstrom. The calculated value of internuclear distance is in good agreement with the experimentally observed internuclear distance of 1.31 angstrom in HCl molecule. This process may be reversed, that is, the atomic radius of H atom may be calculated by subtracting the atomic radius of chlorine from the internuclear distance of HCl molecule. In general, the atomic radius of an atom B in AB molecule can be calculated by measuring the internuclear distance RAB of AB molecule and knowing the atomic radius of atoms A as RB equal to radius of AB minus radius of A. The atomic radii of atoms which do not form diatomic molecules with single bonds are calculated by indirect methods. For example, the single bond radii of nitrogen and oxygen are not obtained from R A minus B equal to RA plus RB minus modulus XA minus XB modulus closed. The bond lengths in N2, that is N triple bond N, and O2, that is O double bond O, because these molecules contain multiple bonds. One half of the internuclear distance of these molecules will correspond to multiple bond radii. For example, the triply bonded radius of nitrogen is 1.10 by 2, that is 0.55 angstrom. Internuclear distance in N triple bond N molecule is 1.10 angstrom. The single bond atomic radii of nitrogen can be obtained by indirect method. In indirect method, the compounds in which N atom is bonded to another atom by a single bond is selected. For example, the internuclear distance between C and N is in CH3NH2 has been found to be 1.47 angstrom. Since the atomic radius of carbon is 0.77 angstrom obtained from C single bond C distance in diamond, the atomic radius of nitrogen is 1.47 minus 0.77 equal to 0.70 angstrom. Multiple bond radii. For multiple bonded atoms, the corresponding radii are called multiple bond radii. For example, carbon has double bonded radius of 0.66 angstrom in ethylene CH2 double bond CH2 and triple bonded radius of 0.60 angstrom in acetylene CH triple bond CH. The carbon has single bond radius of 0.77 angstrom as in ethene CH3 single bond CH3. Similarly, nitrogen has single, double and triple bond radius of 0.70 angstrom, 0.60 angstrom and 0.55 angstrom respectively. As the number of bonds increases, the attraction between the atoms also increases and therefore the atoms approaches close and atomic radius decreases. Atomic radius for C single bond C is 0.77 angstrom. For C double bond C is 0.66 angstrom. For C triple bond C is 0.60 angstrom. Atomic radius for N single bond N is 0.70 angstrom. N double bond N is 0.60 angstrom. N triple bond N is 0.55 angstrom. Hybridization and atomic radius. The state of hybridization also affects the radius of an atom. For example, the carbon hydrogen single bond distance in methane CH4 sp3 hybridization, ethylene CH2 double bond CH2 sp2 hybridization and acetylene CH triple bond CH sp hybridization is different and therefore the atomic radius of carbon is different. For example, CH, C single bond H, internuclear distances are CH4 equal to 1.14 angstrom, CH2 double bond CH2 equal to 1.11 angstrom, CH triple bond CH equal to 1.07 angstrom. For hybridization sp3, S character is 25%. For example, CH4. CH distance is 1.14 angstrom, radius of C is 0.77 angstrom. For sp2 hybridization, S character is 33.3%. Example, CH2 double bond CH2, C single bond H distance is 1.11 angstrom, radius of C is 0.74 angstrom. Hybridization for sp3, sp. S character is 50%. Example, CH triple bond CH, C single bond H distance is 1.07 angstrom, radius of C is 0.70 angstrom. Since the atomic radius of hydrogen is 0.37 angstrom, the atomic radius of carbon in CH4, CH2 double bond CH2 and CH triple bond CH is 0.77 angstrom, 0.74 angstrom and 0.70 angstrom respectively. The decrease in atomic radius of carbon or carbon-hydrogen internuclear distance may be attributed to the increase in S character in going from sp3 25% to sp2 33% to sp 50%. With increase in S character, the electron pair between C and H becomes closer to the nucleus, resulting greater attraction and therefore atomic radius decreases. We learned that the atomic radius is dependent on many factors such as bond order, bond type, oxidation number of atom and crystal structure. While making comparison, we should keep in mind that we compare similar type of radii among atoms in a row or a group. The atomic radii of elements of S and P block elements are given below. Atomic radii in angstrom of main groups S and P. For H, it is 0.37, lithium 1.23, Be 0.89, B 0.80, C 0.77, N 0.70, O 0.66, F 0.64. For helium, it is 1.22, neon 1.60, argon 1.91, krypton 2, xenon left, radium left. Then sodium 1.57, Mg 1.36, Al 1.25, Si 1.17, P 1.10, S 1.04, Cl 0.99. These are all in angstroms. For K, it is 2.303, Ca 1.74, Ga 1.25, Ge 1.22, As 1.21, Se 1.17, Br 1.14. The values for atomic radii of noble gas atoms are van der Waals radii rather than their covalent bonded radii. Second is metallic or crystal radii. This gives the size of the atom in case of metallic elements. In case of metals, a large number of atoms are closely packed and are held together by means of metallic bonds. The close packing of the metal atom is known as crystal lattice or metal lattice, and this packing is different in different metals. The metallic radius may be defined as one half of the distance between the nuclei of two adjacent atoms of a metal in a metallic lattice. The nearest neighboring atoms in a metallic crystal is determined by X-ray diffraction. This is divided by 2 and calculated the metallic radius as radius of metallic is intermolecular distance between two adjacent atoms in metallic lattice divided by 2. For example, the metallic radius of sodium is 1.86 angstrom. The metallic radius are larger than the corresponding single bond covalent radii. For example, the covalent radius of sodium is 1.54 angstrom while its metallic radius is 1.86 angstrom. This is because metallic bond is weaker than a covalent bond, and therefore the metal atoms in a metallic lattice is not drawn as close to each other as in covalent bond. Third is van der Waals radius. Van der Waals radius is defined as one half of the internuclear distance between the adjacent atoms belonging to two nearest neighboring molecules of the same substance in a solid state. It has been observed that there are some weak forces of interaction between two neutral atoms of noble gases atoms and non-polar molecules of various substances. These are known as van der Waals forces, and due to these forces, the noble gas atoms and non-polar molecules are held together, particularly in a solid state. Thus, the van der Waals radius corresponds to the closest approach of two atoms of noble gases or non-polar molecules of other substances which otherwise do not form bonds. The measurements of van der Waals radius for chlorine is the formula for van der Waals is nuclear distance between two non-bonded nearest neighboring atoms divided by 2. Internuclear distance between two chlorine atoms of nearest neighboring molecules is 3.60 angstrom. Van der Waals radius for chlorine is 3.620 divided by 2 equal to 1.80 angstrom. The van der Waals radii of some atoms are given in below along with their covalent radii. As evident from that table, the van der Waals radii are larger than the covalent radii. This is obvious because in the formation of covalent bond, the atoms come close to each other due to the overlapping of orbitals. On the other hand, van der Waals forces existing between atoms or molecules are weak and the atoms are at larger distances. Therefore, the nuclear distance in case of atoms held by van der Waals forces is more than that between covalently bonded atoms. Consequently, van der Waals radii are larger than covalent radii. There are some elements where covalent and van der Waals radii are given. For nitrogen, covalent radii is 0.77 and van der Waals is 1.50. For oxygen, covalent is 0.74 and for van der Waals it is 1.40. For fluorine, covalent is 0.72, van der Waals is 1.35. For neon, covalent is not given and one because neon is a noble gas, so that's why van der Waals is given 1.31. Phosphorus covalent is 1.10, van der Waals is 1.80. For sulfur covalent is 1.04, van der Waals is 1.90. For chlorine covalent is 0.99 and van der Waals is 1.80. For argon covalent is not given, van der Waals is 1.74. Van der Waals radii is greater than covalent radii. Then Bragg-Slater radii. Bragg and Slater proposed set of internally consistent atomic radii. These radii can be added irrespective of the bond type involved in the interaction between two atoms to give good correlations with observed internuclear distances. In general terms, the Bragg-Slater radii represent the radii of inner cores of electrons, which in turn determine how closely two atomic species can approach each other. The Bragg-Slater radii of elements of second period are given ahead. Element is lithium. Covalent radius is 1.23, Bragg's radius is 1.45. For beryllium, covalent radius is 0.89 and Bragg's radius is 1.05. For boron, covalent radius is 0.80, Bragg's radius is 0.85. For carbon, covalent radius is 0.77, Bragg's radius is 0.70. For nitrogen, covalent radius is 0.70. For Bragg's, it is 0.65. For oxygen, covalent radius is 0.6066. For Bragg's radius, it is 0.60. For fluorine, covalent radius is 0.64 and Bragg's radius is 0.50. Periodic trends in size. Let us discuss the periodic trends in a period and a group. First, variation of atomic radii in a period. In general, the atomic radii decreases as we move from left to right in a period in the periodic table. For example, in the second period, the atomic radii decreases from lithium to fluorine through beryllium, boron, carbon, nitrogen and oxygen. In the table, the radius are given from lithium to fluorine. For lithium it's 1.23, for beryllium it's 0.89, for boron it's 0.80, for carbon it's 0.77, for nitrogen it's 0.70, for oxygen it's 0.66, for fluorine it's 0.64. Explanation. This may be explained on the basis of increasing nuclear charge along a period. With the increase in atomic number from lithium to fluorine, the magnitude of the nuclear charge increases, while the corresponding addition of electron takes place in the same principal shell, that is second. Since the electrons in the same shell do not screen each other from the nucleus, the increase in nuclear charge is not neutralized by the extravalent electrons. As a result, electrons are pulled closer to the nucleus by the increased effective nuclear charge and thereby cause a decrease in the size of the atom. In this way, the atomic size goes on decreasing across the period. Note: the variation in atomic radii in a period can easily be explained on the basis of effective nuclear charge instead of nuclear charge. Effective nuclear charge is equal to actual nuclear charge minus screening constant. The effective nuclear charge increases regularly in a period as given below, and therefore there is a regular decrease in the radii of atoms from left to right. For lithium, nuclear charge is 3 and effective nuclear charge is 1.30. For beryllium, nuclear charge is 4, effective nuclear charge is 1.95. For boron, nuclear charge is 5, effective nuclear charge is 2.60. For carbon, nuclear charge is 6, effective nuclear charge is 3.25. For nitrogen, nuclear charge is 7, effective nuclear charge is 3.90. For oxygen, nuclear charge is 8, effective nuclear charge is 4.55. For fluorine, nuclear charge is 9, effective nuclear charge is 5.20. Second, variation of atomic radii in a group. The atomic radii of elements increase from top to bottom in a group. Explanation. In moving down a group, the nuclear charge is increasing with increase in atomic number, and we expect that the size of atom should decrease. However, while going from one atom to another, there is increase in the principal quantum level. Although the number of electrons in the outermost shell remains the same, the effect of increase in the size of the electron cloud is more pronounced than the effect of increased nuclear charge. Consequently, the distance of the outermost electron from the nucleus gradually increases down a group. In other words, the size of the atom goes on increasing as we move down a group, as illustrated in table. For alkali metal groups, for lithium, outermost configuration is 2s1, atomic radii is 1.23 angstrom. For sodium, outermost electronic configuration is 3s1, atomic radii is 1.57. For potassium, outermost configuration is 4s1, atomic radius is 2.03. For rubidium, outermost configuration is 5s1, atomic radius is 2.16. For cesium, outermost configuration is 6s1, atomic radius is 2.37. The periodic verification of the atomic radii of the elements with atomic numbers are given in the figure. It is clear from the figure that alkali metal atoms are at maximum of the plot and halogen atoms are at minima. The values for noble gases are not plotted because they correspond to van der Waals radii. This shows that the largest atom in any period are the alkali metals and the smallest are the halogens. Fourth, ionic and crystal radii. The ionic radii corresponds to the radii of ions in anionic crystals. The ions are formed as a result of addition or removal of electrons from the outermost shell of atoms. The ions formed by the loss of electrons acquire positive charge and are called cations, while the ions formed by the gain of electron acquire negative charge and are called anions. Ionic radius may be defined as the effective distance from the nucleus of the ion up to which it has an influence in the ionic bond. Measurement of ionic radius. The X-ray studies give the distance between the nuclei of adjacent positive and negative ions in the crystal. If the ions are regarded as spheres, the internuclear distance may be taken equal to the sum of the radius of the cations and the radius of the anions. For example, internuclear distance of Na positive Cl negative is 2.76 angstrom, which corresponds to the sum of ionic radii of Na positive and Cl negative ions. Radius of Na positive plus Cl negative is equal to 2.76 angstrom. But the problem of assigning different values to constituting ions is not simple unless the radius of any one ion is known. We cannot calculate the radius of the other ion. Several methods have been proposed to calculate the ionic radii of ions. Out of the various methods, Pauling's method is most widely accepted. Pauling's method for calculation of ionic radii. This method is based on the calculation of ionic radii from the observed internuclear distances from a set of ionic compounds which have the cations and anions. isoelectronic. That is, their cations and anions have the same number of electrons. He selected 4 ionic compounds with NaF, KCl, RbBr, and CSI. In each salt, the cation and anion are isoelectronic. For example, in NaF, both Na positive and F negative ions have 10 electrons and have the configuration 1s2, 2s2, 2p6. Similarly, in KCl, RbBr, and CSI, the cations and anions have 18, 36, and 54 electrons respectively. Polling suggested that for the isoelectronic ions, the radius of an ion is inversely proportional to the effective nuclear charge, that is Z effective of the ion. That is, radius is inversely proportional to Z effective. Z effective can be written as Z minus S, where Z is nuclear charge and S is screening constant. Then, avoiding the sign of proportionality, we used a constant. Then the formula is R equal to C divided by Z minus S, where C is proportionality constant and it is same for two isoelectronic ions. The effective nuclear charge Z effective can be calculated by subtracting a screening constant from the actual nuclear charge. The value of screening constant is calculated from Slater's rule. Let us consider an example of sodium fluoride. The internuclear distance in NaF has been found to be 2.31 angstrom, so that both Na positive and F negative ions are isoelectronic, having 10 electrons and have the same value of screening constant. According to Slater's rule, the screening constant for both the ions have been found to be 4.15, that is, S is equal to 4.15. The actual nuclear charge of Na positive and F negative are 11 and 9 respectively, so that the effective nuclear charge of Na positive is 11 minus 4.15, that is 6.85. The effective nuclear charge for F negative is 9 minus 4.15, that is 4.85. Thus, according to Pauling, radius of Na positive is equal to C divided by 6.85, radius of F negative equal to C divided by 4.85. Substituting the values of radius of Na positive and radius of F negative in equation, we get C divided by 6.85 plus C divided by 4.85 equal to 2.31. After solving this equation, C equal to 6.56, using the above value of C, radii of Na positive and F negative are, radius of Na positive is 0.96 angstrom, radius of F negative is 1.33 angstrom. With the help of above procedure, the radii of most of the cations and anions have been determined. Then, size of cations and the anions. Size of the cations. In general, the size of a cation is smaller than a neutral atom. This is due to the fact that with the removal of electrons from an atom, the magnitude of nuclear charge remains same while the number of electrons decreases. As a result, the nuclear charge now acts on lesser number of electrons. In other words, the effective nuclear charge per electron increases and the electrons are more strongly attracted and are pulled towards the nucleus. This causes a decrease in the size of the atom. For example, atomic radii of Na is 1.54 angstrom. Ionic radii of Na positive is equal to 0.95 angstrom. Atomic radius of K is equal to 1.96 angstrom. Ionic radii of K positive is 1.33 angstrom. Size of the cation and the anion. In general, the negative ion or anion is always larger than that of the corresponding atom. The negative ion is formed by the gain of one or more electrons in the neutral atom, and the number of electrons increases while the magnitude of the nuclear charge remains the same. As a result, the same nuclear charge acts on large number of electrons than are present in the neutral atom. In other words, effective nuclear charge per electron is reduced and the electron cloud is held less tightly by the nucleus. This causes an increase in size and the anions are larger in size than the corresponding atoms. For example, atomic radii for Cl is 0.99 angstrom, ionic radius for Cl negative is 1.81 angstrom. Atomic radius for Br is 1.14 angstrom. Ionic radius for Br negative is 1.95 angstrom. Isoelectronic ions. Isoelectronic ions are ions of different elements which have same number of electrons but differ from one another in magnitude of the nuclear charge. A set of species having the same number of electrons is known as isoelectronic series. For example, in the following series of ions, all the species have 10 electrons. Ions are N3 negative, whose nuclear charge is +7. Second is O2 negative, whose nuclear charge is +8. Next is F negative, whose nuclear charge is +9. Then Na positive, nuclear charge is +11. Then Mg2 positive, nuclear charge is +12. Then Al3 positive, nuclear charge is +13. Similarly, in the following series of isoelectronic ions, all the species have 20 electrons. Ions and nuclear charge. Ion is P3 negative, nuclear charge +15. S2 negative, nuclear charge is 16. Cl negative, nuclear charge is 17. K positive, nuclear charge is 19. Ca2 positive, nuclear charge is 20. Periodic trends in ionic radii. Variation of ionic radii in a period. For an isoelectronic series, ions having same number of electrons, the ionic radius decreases as the nuclear charge increases. Explanation. In an isoelectronic series, there is an increase in nuclear charge and therefore the attraction of the same number of electrons increases. As a result, the electrons are pulled more and more strongly and thus ionic radius decreases. There is a table given, that is ion is N3 negative, nuclear charge +7, radius in angstrom is 1.72. For O2 negative, nuclear charge is +8, radius is 1.4 angstrom. 40 angstrom. For fluor F negative, nuclear charge is +9, radius is 1.26 angstrom. For Na positive, nuclear charge is +11, radius is 0.95 angstrom. For Mg2 positive, nuclear charge is +12, radius is 0.65 angstrom. For Al3 positive, nuclear charge is 13, radius is 0.50 angstrom. All ions have known configuration containing 10 electrons. Second, variation of ionic radii in a group. As we go down a group, the ionic radii increases with increase in atomic number as shown in the table, like atomic radius. Explanation. This is mainly due to increase in the principal quantum levels. The effect of increase in principal quantum level is more pronounced than the effect of increased nuclear charge. The table is ion Li positive, ionic radius is 0.60 angstrom. For Na positive, 0.95 angstrom. For K positive, 1.33 angstrom. Rb positive, 1.48 angstrom. Cs positive, 1.69 angstrom. Explanation. This is mainly due to increase in principal quantum levels. The effect of increase in principal quantum levels is more pronounced than the effect of increased nuclear charge. Ionization energy. The ionization energy gives a measure of the ease with which an atom can lose an electron and change into a cation. Ionization energy of an element is defined as the amount of energy required to remove the most loosely bound electron from an isolated gaseous system. For example, M is any gas plus ionization energy, then it is converted into M positive gas plus electron of that gas. Ionization energy is also called as ionization potential because it is measured as the amount of potential needed to remove the most loosely held electron from the gaseous atom. The experimental values of ionization energies are determined either by spectroscopic method or by passing an electric current of gradually increasing intensity through the vapors of the elements in a discharge tube. It is expressed in terms of either kilocalorie per mole or kilojoule per mole or electron volt per atom. Thus, the ionization energy gives the ease with which electron can be removed from an atom. Evidently, the smaller the value of ionization energy, the easier it is to remove the electron from the atom. Factors on which ionization energy depends. The magnitude of ionization energy for an atom depends upon the following factors. First is size of the atom. The ionization energy depends upon the distance between the electron and the nucleus, that is size of the atom. The attractive force between the electron and the nucleus is inversely proportional to the distance between them. Consequently, as the size of the atom increases, the outermost electrons are less tightly held by the nucleus. As a result, it becomes easier to remove the electron and therefore ionization energy decreases with the increase in atomic size. Second, charge on the nucleus. The attractive force between the nucleus and the electron increases with increases in nuclear charge. This is because the force of attraction is directly proportional to the product of the charges on the nucleus and that on the electron. Therefore, with the increase in nuclear charge, it becomes more difficult to remove an electron and ionization energy increases. Third, screening effect of the inner electrons. In multi-electron atoms, the outermost electrons are shielded and or screened from the nucleus by the inner electrons. This is known as shielding or screening effect. As a result of this, the outermost electron does not feel the full charge of the nucleus. The actual charge felt by an electron is termed as effective nuclear charge. Effective nuclear charge Z effective is total nuclear charge minus screening constant, where screening constant takes into account the screening effect of the inner electrons. If the number of electrons in the inner shell is large, the screening effect will be large. As a result, the nucleus electron force will be less. Consequently, ionization energy will decrease. Thus, if other factors do not change, an increase in the number of electrons tends to decrease the ionization energy. Fourth, penetration effect of electrons. It is well known that in case of multi-electron atoms, the electrons in the s orbital have the maximum probability of being found near the nucleus, and this probability goes on decreasing in case of p, d and f orbitals. In other words, s electrons are more penetrating towards the nucleus than p electrons, and the penetration power decreases in a given shell. Same value of n. In order, S has more penetrating power than P, has more than D, has more than F. Now, if the penetration of the electron is more, it will be closer to the nucleus and will be held firmly. Consequently, ionization energy will be high. This means that ionization energy decreases with the increase in penetration power of the electron. Thus, for the same shell, the required ionization energy would be more to remove an s electron than to remove a p electron, which in turn will be more than that for the removal of d electron and so on. Fifth, electronic arrangement. The ionization energy also depends upon the electronic configuration of the atom. It has been observed that certain electronic configurations are more stable than the others. For example, half-filled and completely filled shells have extra stability associated with them. Consequently, it is difficult to remove electrons from these stable configurations and ionization energy is high. This may be illustrated by the following examples. First, the noble gas have the most stable electronic configuration ns2np6 in each period and have highest ionization energies. Second, the elements like Be 1s2 2s2 and Mg 1s2 2s2 2p6 3s2 have completely filled orbitals and their ionization energies are large. Third, the elements like N 1s2 2s2 2px1 2py1 2pz1 and P 1s2 2s2 2p6 3s2 3px1 3py1 3pz1 have the configurations in which the orbitals of same subshell are exactly half filled and are also stable. Hence, they need large energy to remove the electrons, that is, their ionization energies are high. Thus, the more stable of electronic configuration, the higher is the ionization energy. Variation of ionization in a periodic table. Ionization energy provides another example for understanding periodicity among the elements. The ionization energies for elements of S and P block are given in a table. For example, for hydrogen it is 1312, for lithium 520, beryllium 899, boron 800, carbon 1086 and so on. It can be seen from the figure that in each period the maxima are found at the noble gases while minima are found at alkali metals. Thus, the metal of group 1 with 1 electron at outermost s orbitals are easy to ionize, while the noble gases with ns2 np6 configuration are the most difficult to ionize. The following periodic trend has been observed. A. Variation along a period. In general, the ionization energy increases with increasing atomic number in a period. This is quite clear from the values of ionization energy of a second row element. The general increase along a period can be explained on the basis of atomic size and nuclear charge. We know that first, on moving across a period from left to right, the nuclear charge increases. Second, the atomic size decreases along a period through though energy level remains the same. As a consequence of increased nuclear charge and simultaneous decrease in atomic size, the valence electrons are more and more tightly held by the nucleus. Therefore, more and more energy is needed to remove the electron and hence ionization energy keeps on decreasing. Elements for lithium, ionization energy is 520.3. For beryllium, it is 899.5. These are all in kilojoule per mole. For boron, it is 800.6. For carbon, it is 1086.4. For nitrogen, 1402. For oxygen, 1314. For fluorine, 1684. For neon, 2080. However, some irregularities in the general trend has been noticed. These are due to half-filled and completely filled configurations which have extra stability. To illustrate this, let us consider the variation of ionization energy in second period, going from one element to another, from lithium to beryllium. On moving from lithium to beryllium, there is an increase in ionization energy, and this is due to increased nuclear charge and smaller ionic atomic size. From beryllium to boron, although the nuclear charge of boron is more than beryllium, yet there is slight decrease in ionization energy from beryllium to boron. This is due to the fact that first, in boron, the last electron goes to 2p orbital, which is at a slightly higher energy than 2s and is easy to be removed. Second, the electronic configuration of boron 1s2 2s2 2p1 is less stable than that of beryllium 1s2 2s2, which has completely filled orbitals. As a result, the 2p electrons of B, that is boron, is not tightly held by the nucleus as 2s electrons of beryllium, and hence ionization energy of boron is less than that of beryllium. Boron to carbon to nitrogen. As we move from boron to carbon to nitrogen, the ionization energy keeps on increasing due to increasing nuclear charge and decreasing atomic size. From nitrogen to oxygen. Oxygen, the element next to nitrogen, has slightly smaller ionization energy as compared to that of nitrogen. It is due to the fact that the electronic configuration of nitrogen atom 1s2 2s2, 2px1, 2pxy1, 2pz1, in which each 2p orbital is half-filled, is more stable than that of oxygen 1s2, 2s2, 2px2, 2py1, 2pz1. Therefore, ionization energy of nitrogen is more than that of oxygen. Oxygen to fluorine to neon. The ionization energy decreases from oxygen to fluorine to neon because of the increased nuclear charge and decrease in size. Neon, the noble gas, has the maximum ionization energy in the period due to the stable Ns2 Np6 electronic configuration. Similar variations in ionization energies of the elements of third period have also been observed. B. Variation down a group. Within a group, there is a gradual decrease in ionization energy in moving from top to bottom. This is clear from the ionization energy values of the elements of the given groups as given in the below table. That is, for lithium, ionization energy is 520.3 kilojoule per mole. For sodium, it is 495.8. For potassium, it is 418.9. Rubidium 403.2. Cesium 374.1. This decrease in ionization energy down a group can be explained in terms of net effect of the following factors. In going from top to bottom in a group, the nuclear charge increases. Second, there is a gradual increase in atomic size due to an additional main shell. Third, there is an increase in shielding effect on the outermost electron due to an increase in the number of inner electrons. The effect of increase in atomic size and the shielding effect is much more than the effect of increase in nuclear charge. As a result, the electron become less and less firmly held to the nucleus as we move down the group. Hence, there is a gradual decrease in the ionization energies in a group. Successive ionization energies. The atom may not only lose one electron, but more than one electron also. Therefore, it is essential to specify the definition of ionization energy for each electron which is to be removed. The energies required to remove subsequent electrons from the atom in a gaseous state are known as successive ionization energies. The term first, second, third ionization energy refers to the removal of first, second, third electron respectively. These changes may be represented as follows. M is a gaseous metal. First ionization energy is given, then M positive gas plus electron is found. Then M positive is ionization, that is second ionization energy. N2 positive is gained plus electron. Then N2 positive, in it is given ionization energy third, and then we got M3 positive plus electron. Here ionization first, second and third represent first, second and third ionization energies respectively. For example, the first and second ionization energies for lithium may be given as: first ionization energy is 520 kilojoule per mole, second ionization energy is 7298 kilojoule per mole. As can be seen, the second ionization energy are very much higher than the first ionization energies. This is mainly due to the fact that after the removal of the first electron, the atom changes into monovalent positive ions. In the ion, the number of electrons decreases but the nuclear charge remains the same. As a result of this, the remaining electrons are held more tightly by the nucleus and it becomes difficult to remove the second electron. Hence, the value of second ionization energy is greater than the first. In the same way, the removal of the second electron will result in the formation of a dispositive ion, and attraction between the nucleus and remaining electrons increases further. This results into higher value of third ionization energy than second. The successive ionization energies to the first 14 elements are shown in the table. The ionization energies to the right of the stepwise lines correspond to the removal of electrons from field configurations of the atom. As is clear from the table, for each atom there is large increase in the energy. After all, the outermost electrons have been removed. For example, in case of sodium, the first ionization energy corresponding to removal of valence electron is 496 kJ per mole, but the second ionization energy corresponding to removal of electron from field electronic configuration is 4564 kJ per mole, almost 10 times. Similarly, for magnesium, the first ionization energy is 737 kJ per mole and second ionization energy is 1447 kJ per mole. However, the third ionization energy value is 7738 kJ per mole, which is over 5 times as much as the second ionization energy. This is because, after all the electrons in a valence shell have been removed, the next electron must be removed from the core of the atom having stable noble gas configuration. Therefore, ionization energy becomes very high. Electron affinity. Just as energy is required to remove an electron from an atom, energy is released when an electron is added to a neutral atom. This is called the electron affinity. Thus, the amount of energy released when an electron is added to an isolated gaseous atom is called the electron affinity. The process may be expressed as X is any gas plus electron is given, then X negative gas is formed and energy is found. For example, chlorine plus 1 electron is chlorine negative plus Ea, that is electron affinity. As the definitions implies, the magnitude of the electron affinity measures the ability of an atom to hold an additional electron. If an atom has more tendency to accept an electron, large energy will be released. Consequently, electron affinity will be high. On the other hand, if an atom has less tendency to hold the electron, small amount of energy will be released, leading to a small value of electron affinity. Electron affinities can be positive or negative. When an energy is released during the addition of an electron of an atom, the electron affinity is taken as positive. Electron affinities are expressed in kilojoule per mole. Factors on which electron affinity depends. There are many factors which govern the electron affinity, but the following are some important factors on which it mostly depends. Firstly, nuclear charge. The electron affinity increases as the nuclear charge increases. This is due to greater attraction for the incoming electron if nuclear charge is high. Size of the atom. With the increase in size of the atom, the distance between the nucleus and the incoming electron increases, and this results in lesser attraction. Consequently, the electron affinity value will decrease. Electronic configuration. The element having stable electronic configuration of half and completely filled valence subshells show very small tendency to accept additional electron, and thus electron affinities are low or almost zero in certain cases. Periodic trends. Due to lack of sufficient data, the changing trends in electron affinities on moving along the period tables are less well defined than those for ionization energies. However, it has been observed that the electron affinity in general increases from left to right in a period and decreases from top to bottom in a group. These variations are discussed below. First, variation down a group. On moving down the group, the atomic size and nuclear charge increases, but the effect of increase in atomic size is much more pronounced than that of nuclear charge, and thus the additional electron feels less attraction by the large atom. Consequently, electron affinity decreases. This is clear from the decrease of electron affinity in going from chlorine to bromine and to iodine. Here, in the table given that for hydrogen, electron affinity is 72.8, for lithium 59.8, for sodium 53.1, potassium 48.4. For beryllium, magnesium and calcium, it is almost zero. For beryllium, for boron, aluminium and gallium, boron 83, aluminium 50.2, gallium 35.7, carbon 127.5. For nitrogen, it is 0. Silicon 119.6, germanium 115.8. For noble gases, it is 0. And there is exception that chlorine has more electron affinity than fluorine. B. Variation along a period. On moving across a period, the size of an atom decreases and nuclear charge increases. Both these factors result into greater attraction for the incoming electron. Therefore, electron affinity in general increases in a period from left to right. However, certain irregularities observed in the general trend. These are mainly due to the stable electronic configurations and certain atoms. There are some important features of electron affinities of elements. These are: first, halogens have the highest electron affinities. The electron affinities of the halogens are the highest. This is due to the fact that halogens have the general electronic configuration of Ns2 Np5 and have only one electron less than the stable noble gas configurations. Thus, they have very strong tendency to accept an additional electron, and their electron affinities are therefore high. Second, electron affinity of noble gases are 0, while those of beryllium, magnesium, nitrogen, and phosphorus are almost 0. The electron affinity of noble gases are 0. This is because they have stable electronic configuration of Ns2 Np6, and thus they have absolutely no tendency to take an additional electron. This means that the incoming electron does not feel any attraction for the nucleus. Thus no energy is released and their electron affinities are 0. Similarly, the low, almost 0, electron affinity values for beryllium, magnesium, nitrogen, and phosphorus can be explained due to the extra stability of fully filled 2s and 3s orbitals in beryllium 2s2, magnesium 3s2 respectively, and of half-filled 2p and 3p orbitals in nitrogen and phosphorus respectively. Therefore, their configurations show little tendency to gain any electron, and hence their electron affinities are almost 0. Third, electron affinity of fluorine is unexpectedly less than that of chlorine. As already explained, the electron affinity in general decreases from top to bottom in a group. However, it is observed that fluorine atom has unexpectedly less electron affinity than chlorine atom. The electron affinity values for the halogens are as shown in the figure. The low value of fluorine atom is due to the very small size of fluorine atom. As a consequence of a small size, there are strong inter-electronic repulsions in the relatively compact 2p subshell of fluorine, and thus the incoming electron does not feel much attraction. As a result, its electron affinity value is small. On the other hand, the electron affinity of chlorine atom is larger than fluorine atom, where the electron is added to a relatively large 3p orbital, which can easily accommodate the additional electron. It may be noted that in general, electron affinities for some third period elements, that is phosphorus, silicon, chlorine, are greater than the corresponding second period members, that are nitrogen, oxygen, fluorine respectively. This is due to the smaller size of the atoms of the second period elements, which would produce larger electron repulsions from the additional electron. This effect is much more pronounced in the small fluorine atom as discussed above. Successive electron affinities. Like ionization energies, the second and higher electron affinities are also possible. However, the second electron is added to a negatively charged ion, and the addition is opposed by Coulombic repulsions. The energy has to be supplied to force the second electron as shown below for oxygen atom. Oxygen in gaseous form, 1 plus 1 electron, oxygen negative. Ionization energy is first 140.9 kilojoule per mole. Energy released. O negative gas, one more electron is added, O2 negative. Second ionization energy is minus 770 kilojoule per mole energy required. In other words, the second and higher electron affinities would have negative values, since the first electron affinity in which energy is released is taken as positive. For example, the first and second electron affinities of oxygen and sulfur are: oxygen first is 140.9 kilojoule, second minus 770 kilojoule. For sulfur, first is 200.7 kilojoule and second is minus 333 kilojoule. Next is electronegativity. When a covalent bond is formed between two homonuclear atoms, the shared pair of the covalent bond lies exactly midway between the nuclei of the two atoms, because both the atoms may have same attraction for these electrons. For example, in molecules such as H2Cl2F2, the electron pair remains exactly at half distance between the two nuclei. However, in the case of covalent bond between dissimilar atoms, heteronuclear molecules, the electron pair may be closer to one atom than the other. This is due to the fact that different atoms have different tendency to attract the bonded pair of electrons towards itself. The tendency of an atom to attract the shared electron pair in a molecule towards itself is called electronegativity. Different atoms have different tendency to attract the bonding electron pair towards themselves. Greater the ability of an atom to attract electron in a bond, larger is the value of its electronegativity. It must be remembered that unlike other atomic properties such as ionization energy and electron affinity, which are related to an individual gaseous atoms, the electronegativity is related to the atom in their bonded state. There is no direct method for measuring electronegativity. However, various attempts have been made to derive a scale of electronegativity for the elements. Some of these are discussed below. First, Pauling scale of electronegativity. In 1932, Linus Pauling was the first to propose a scale of electronegativity. He proposed the scale based on the bond energies in heteronuclear bonds. He suggested that if two atoms A and B had the same electronegativity values, the bond energy of AB bond would be equal to the geometric mean. The mean of the bond energies of AA and BB bonds. For example, the bond energy of AB molecule may be written as EAB equal to under root EAA multiply EBB. This relation is based on the assumption of pure covalent bonds in A2 and B2 and AB molecule. However, he observed that for most of the AB bonds, the actual bond energy is more than the geometric mean of bond energy of EAA and EBB. This means that two participating atoms have different tendencies to attract the shared pair, that is, have different electronegativities. In other words, the bond AB will no longer be purely covalent bond. As a result, there is contribution of ionic structure A positive, B negative, assuming B is more electronegative than A. In addition to pure covalent AB structure, the difference between the actual bond energy of AB and the geometric mean bond energy, that was EAA into EBB under root, is known as excess bond energy. It is a measure of the difference in electronegativities of two atoms A and B. Thus, excess bond energy is equal to EAB minus under root EAA into EBB. The excess bond energy arises due to the resonance between the structures AB and A positive B negative ionic, and is also known as ionic resonance energy. AB covalent is in equilibrium with A positive B negative ionic. B is more electronegative than A. By calculating excess bond energy for different bonds, Pauling suggested the following types of relationships between electronegativities of two atoms XA and XB and the excess bond energy. That is, XA minus XB is equal to 0.18 under root excess bond energy This is in kilocalorie per mole. It may be noted that the constant value 0.18 is valid when the bond energy EAA and EBB are in kilocalorie per mole. When the energies are in electron volt per molecule, the relation becomes XA minus XB is equal to 0.208 under root excess bond energy. In SI units, the relation becomes XA minus XB is equal to 0.088 under root excess bond energy. Therefore, one should be very careful in using this relation. The units of bond energy should be taken into consideration. Assigning an arbitrary value to one of the element, the electronegativities of the other elements could be easily calculated. Pauling assigned the value of 4 to the most electronegative element, fluorine. The Pauling electronegativity value are given in the table for normal elements. These are most commonly used values. For hydrogen it is 2.1, lithium 1, beryllium 1.5, boron 2, carbon 2.5, nitrogen 3.0, oxygen 3.5, fluorine 4, sodium 0.9, magnesium 1.2, aluminum 1.5, silicon 1.8, phosphorus 2.1, sulfur 2.5, chlorine 3, K 0.8, Ca 1, gallium 1.6, germanium 1.8, arsenic 2, Se 2.4, Br 2.8, Rb 0.8, Sr1, In 1.7, Sn 1.7, Sb 1.9, Te 2.1, I 2.4. Disadvantage of Pauling scale of electronegativity. The main disadvantage of Pauling scale is that the bond energies are not known with good degree of accuracy so for many elements. However, the value are relative values. Second, Mulliken's concept of electronegativity. Mulliken in 1934 suggested that the tendency of an atom to compete for the shared pair of electrons in a bond should be the average of ionization energy and electron affinity. Thus, according to Mulliken, electronegativity of an atom is ionization energy plus electron affinity divided by 2, where both ionization energy and electron affinity are given positive values. The physical picture of Mulliken concept is reasonable because the tendency of one atom to attract shared electrons in a bond should be average of the tendency of the atom to hold its own electron and its tendency to attract the additional electron. The Mulliken's value expressed in electron volt have been found to be about 2.8 times as large as Pauling values. Therefore, these values are divided by 2.8 to get the Pauling values, that is x of Pauling is equal to x of Mulliken's divided by 2.8. However, if ionization energy and electron affinity values are expressed in kilojoule per mole, then 1 electron volt is equal to 1.602 into 10 raised to power minus 19 into 6.022 into 10 raised to power 23 joule per mole, that is 96.48 kilojoule per mole. Pauling values can be expressed as x Pauling is equal to x Mulliken's divided by 2.8 into 96.48, or x Pauling is equal to ionization energy plus electron affinity divided by 2 into 2.8 into 96.48, that is ionization energy plus electron affinity divided by 540 kilojoule per mole. Disadvantages of Mulliken's scale of electronegativity. There are two main disadvantages of this scale. First, electron affinity values of only a few elements are known. Second, the electron affinity and ionization energy values changes with valence shell of the element. Third, Allred and Rocho's scale. This concept is based on the electrostatic force of attraction between the electron and its nucleus. The force of attraction is taken as the measure of its electronegativity. The force of attraction between the nucleus of the atom and its valence electrons is governed by Coulomb's law and is given by force is Z effective electron into electron divided by r square, where E is charge of electron, Z star is effective nuclear charge, and r is mean distance from the nucleus, that is r covalent. The effective nuclear charge can be easily calculated by using Slater rule for screening of inner electrons. The forces calculated from above equation were plotted against Pauling scale. From these plots, the following relationship is obtained. x is equal to 0.359 z effective divided by r square plus 0.744. Knowing the value of z effective and r, the electronegativity of any element can be calculated. Disadvantages of Allred and Rocher's scale. The main disadvantage of this scale are: first, the covalent radii of many elements are not available, and second, the Slater rule for calculating effective nuclear charge is empirical. However, this scale gained importance because it does not contain quantities such as electron affinities, bond dissociation energies, which are known as comparatively lesser number of elements. 4. Sanderson's scale of electronegativity. Sanderson proposed a scale of electronegativities based on the compactness of the electron clouds around the nucleus or average electron density of an atom. The average electron density of an atom may be given as d is equal to 3z divided by 4 pi r square. R is covalent radius of an atom in angstrom. Z is nuclear charge. According to Sanderson, the electronegativity is expressed as stability ratio for an atom. The stability ratio is defined as the ratio of the average electron density of the atom to that of ideal electron density of hypothetical isoelectric inert gas atom having same number of electrons. Thus, SR is equal to D divided by DI. D is electron density of the atom. Di is ideal electron density of the hypothetical noble gas having the same number of electrons. The stability ratio of an atom is a measure of its electronegativity. The SR value is similar to electronegativity values obtained by Pauling. These are adjusted to Pauling electronegativity by the equation root x is equal to 0.21 SR plus 0.77. It may be noted that none of the electronegativity scales discussed above has a distinct advantage over the others. For the comparison, the electronegativity values calculated by the various methods in the given table. However, Pauling scale has been most commonly used, and in our further discussion these values will be used. For first hydrogen, Pauling's is 2.20, Allred is 2.20, Mulliken is not given, Sanderson is 2.31. For lithium, Pauling is 0.98, Roche is 0.97, Mulliken is 1.3, Sanderson is 0.86. For beryllium, Pauling is 1.57, Allred Roche's is 1.47, Mulliken's is not given, Sanderson's is 1.61, and so on. Then Mulliken's and Jeffy's scale. Mulliken and Jeffy have also proposed a new scale which takes into account the role of hybridization while calculating the electronegativities based on ionization energy and electron affinity. However, it has not been discussed in the present text. Factors affecting the electronegativity. Electronegativity of an atom is not a fixed quantity but depends upon a large number of factors both on isolated as well as bonded atoms. Some of the most factors affecting the electronegativity values are given ahead. First, oxidation state. The electronegativity of an atom varies from one bonding state to another depending upon the oxidation state of the atom in a molecule. In general, the electronegativity increases as the positive oxidation state of the atom increases. This is obvious because with the increase in positive oxidation state, the tendency to attract the electrons will increase. For example, Pauling electronegativity value for Ti first is 1.62, whereas it is about 2.04 for Ti third. Some common examples are SN second, it is 1.80, SN4 1.96, Fe second is 1.83, Fe third is 1.96, copper first is 1.90, copper second is 2. For anions, however, the electronegativity decreases with the increasing negative charge of the ion. This is due to the fact that a more negatively charged ion will attract less electrons than a less negatively charged or neutral ion. Second, Type of hybridization. The type of hybridization also affects the electronegativity of an atom. We have learned that s orbitals are nearer to the nucleus than p, d and f orbitals because of their higher penetration power. Therefore, s orbitals will have greater electron attracting power or electronegativity. In other words, the electronegativity increases with the increasing s character of the hybrid orbitals. This can be easily illustrated by taking the example of carbon. For methane, hybridization is sp3, s character is 25%, electronegativity is 2.48. For ethylene, hybridization is sp2, s character is 33%, electronegativity is 2.75. For acetylene, hybridization is sp, s character is 50%, electronegativity is 3.29. The S character increases in the order CH, methane, ethylene, and acetylene. And the electronegativity of carbon in these compounds also increases. Similarly, for nitrogen atom, the value of the electronegativity are 3.68, 3.94, and 4.67, or sp3, sp2, and sp hybridization respectively. Third, nature of substituents. The electronegativity of group varies with the nature of the substituents. This is due to the inductive effect of the substituent groups. For example, CH3 equal to 2.30, CCl3 equal to 3.30, CF3 equal to 3.35. In these cases, the electronegativities of these groups will be the electronegativity of carbon as it is adjusted by the presence of substituents 3H, 3Cl or 3F atoms. These values are based on dipole moment, atomic electronegativity and kinetic data. Periodic verification of electronegativity. The electronegativity generally increases on moving across a period from left to right. This is primarily due to the decrease in atomic size and increase in effective nuclear charge. As a result of increase in effective nuclear charge, the attraction for the electrons increases. Electronegativity generally decreases from top to bottom in a group as atomic size increases and the bonding electrons become away from the nucleus. Thus, the alkali metals of group 1 have the lowest electronegativities and the halogens of group 7 have the highest electronegativities. Further inspection shows that the non-metals on the right hand side of the periodic table have high electronegativities while the metals on the left hand side have low electronegativities. In general, as an approximation, elements with electronegativity 2.0 or greater are non-metals while those with electronegativity less than 2.0 are metals. It is clear that the electronegativity generally increases on moving across a period from left to right and decreases on moving down a period. Thank you.